Thank you for the introduction, and thank you to the organizers for organizing such a nice workshop. It's really a pleasure to be here in Helsinki. This is my first time in Finland also, so I'm liking it a lot. And so I'm Kamal Choudhary from NIST, National Institute of Standards and Technology, and it's a part of the United States Department of Commerce. I'm going to talk to you about something called Jarvis machine learning, which I'm working on the Jarvis project for the last 3-4 years now. And I'd like to also acknowledge the other collaborators, James Hickman, Brian, and Francesca. So Jarvis is a part of something called Materials Genome Initiative at NIST, and it has several components such as force field, density functional theory, and machine learning. I'm going to focus mainly on the machine learning part today. So really, I say it's not data-driven, it's funding-driven science, I think, nowadays. So it's mainly our funding comes from the Materials Genome Initiative and the National Quantum Initiative. And that is the funding perspective, but definitely the science part of it, what I'm fascinated about is we as a scientist are working for years, right? But the question of unification is still unsolved to me. For example, you take a periodic table element, like 5 of them, and combine in a particular structure, you cannot still tell, like, what would be the result of it. So how do you solve this problem? It's a huge dimension, chemical and structural space there. How do we solve this? Experiments, no way. Just taking out of the option. Computation like density functional theory, a classical force field. Again, it says there's a transferability of classical force field. There's a length and time scale problem for density functional theory and other atomistic approaches. So we can't go that route too. How about machine learning? So I'm optimistic and hopeful that that machine learning can help at least solving some problem for this unification. So these are sort of the 3 different websites. So in DFT, we have around 30,000 3D bulk structures and around 1,000 2D materials, and around more than 500,000 properties calculating density functional theories. You can go on the DFT part and click on certain elements, hit search, and it shows you different properties of the materials with detailed band structure, dielectric function, all these other properties. For classical force field part, there is, suppose you want to simulate some system like nickel aluminum with lamps or molecular dynamic simulations. You go to the website, if you click, for example, nickel aluminum, it gives you all the available potentials, interatomic potentials, and other data such as elastic constant and other calculated and deposited there so that you can choose a particular potential. In the machine learning part, you can put the crystallographic information, and if you hit send there, it predicts the properties just using machine learning and based on the trained model. So it actually started, maybe I can use this one. Okay, so we actually started with Jarvis force field. So in my PhD, I used to develop classical force field, and I had this problem that I don't know how many potentials are available. So I just, for my personal purpose, I want to make a sort of, small data set so that I can go and take a look whether this potential is available or not. So, and there's a problem. You don't know whether potentials developed for some materials can be transferable for other material. So we made this overall workflow so that we have around 100 force field there and around 20 to 30,000 lamps calculation database where you can go and see, for example, for aluminum, there are like 30 potentials. So you can choose which potential change based on the calculated properties and compare to density functional theory, for example. And we did similar thing for like vacancy formation energy and surface energies as well. So this part is called Jarvis-FF. And comes in 2017, we launched Jarvis density functional theory, which is started with the discovery of 2D materials. So we know that most of the DFT databases you might be aware of, like Materials Project, AFlow, OQMD, they use PB functional constantly for all classes of material. So if you use, for example, van der Waals material, this will be lattice parameter error. It will be error in the lattice parameter. So we use this very simple methodology that if it's a van der Waals material, if you use PB, it will give you error. It's the converse true. So if there's an error, it should be van der Waals material, right? Very simple hypothesis. And we found that using this very simple hypothesis that this method of identifying 2D materials works more than 90% accurately using the exfoliation energy calculations. We also have this something called meta-GGA dielectric function and band gap database, where we know that the conventional density functional theory is really not good for predicting DFT band gaps. And For solve this problem, we can use hybrid functional and stuff like that, but again, it's a very time consuming. So we find a sweet spot between computational expense as well as the predictive accuracy. So we chose this TB-MBJ formalism, and we generated the dielectric function, frequency-dependent dielectric functions, and the band gas for around 20,000 materials there. And the whole data set is again available. Then we discovered something called topological materials using something called spin orbit spillage, where we compared the wave functions of a material with and without spin orbit coupling. And at each k point, we calculate something called spillage. So this is almost accepted now. And so we found out more than 2,000 topological materials out of 30,000 in the database. We have something using this dielectric function approach, we calculate the absorption coefficient and something called spectroscopy limited maximum efficiency, which is similar to solar cell efficiency. And we made a database of that. And finally, because we converge for each material the k points and plane wave cutoff, we can have a database of those two. And since we have the database of all this classical force field and density functional theory, we developed something called classical force field inspired descriptors, which I want to talk about today for learning and those data. First, I'd like to mention something. I think in the last discussion, there was a discussion about the explainable AI. And this slide I have bought from something called DARPA agency. So you can see, for example, there are several machine learning algorithms, and there's a balance between prediction accuracy and explainability. If you are just an engineer at Google, you might be happy with something with complete high accuracy. That's what you care. But if you're a scientist, you might have something worried about explainability as well. So I tend to believe this decision tree and ensemble-based methods should generally have something like feature importance, partial dependence plot, and those kind of things, which makes the AI a little bit at least explainable, if not completely giving all the explanation. And for this method, which I'm going to use, is called gradient boosting decision trees, which is an ensemble of decision tree models. So, I mean, neural networks have been really very popular in this machine learning community, but recently there have been people using this gradient boosting decision tree, and they also find it very successful. And for the people, there was some, who are beginners in this field, I highly recommend this book, Elements of Statistical Learning, which I find very informative. And one of the package for this is the LightGBM. It's a Microsoft package. So you can try that for whatever model you're using. Instead of just using scikit-learn or TensorFlow, I would also invite you to use this Microsoft LightGBM package, which I find very useful. So let's talk about our descriptors. So I call it classical force field inspired descriptors. It has like several components. So first is the chemistry. So there was on the Monday, I think, there was a discussion like, how do you tackle different chemistry? If you have multi-component system, how do you tackle such huge space of descriptors? So one of the way to solve this, like average chemical descriptors. Suppose you have moly disulfide system, and it has 2 moly atoms and 4 sulfur atoms. What you can do is take the electronegativity average of moly, 2 moly, and 4 sulfur. This is one number, right? That one number is average electronegativity descriptor for the whole system. You can similarly take, for example, heat of fusion, atomic radii, van der Waals radii, and all these kind of things. And this average descriptor will give you, and we thought all of it, we spent like 1.5 years to develop this descriptor, and we came 430 such chemical descriptors for uniquely identifying the chemistry of the substance. But suppose you have aluminum oxide. Aluminum oxide has both alpha and big CBI phase. You cannot distinguish them based on only chemical descriptor. You have to add structural descriptors. For structure-wise, so there are 3 kinds of structure descriptor we use. First is definitely the radial distribution functions. So if you take, for example, up to 0 to 10 angstrom, all the atomic bond length, and you bin them basically, then what you get is something called radial distribution function. And if you take from 0 to 10 angstrom, and with 0.1 angstrom bin is 100 descriptors. We can also have 3 body term, and you can bin them as the angles, and this gives you 180 descriptors. And similarly, you can take 4 body terms. In terms of dihedral, it gives you dihedral angle distribution. In addition to that, suppose you have a charge defect in the system. For that, we have something pseudopotential charge distribution. For example, if you use VASP, there's a pseudopotential, right? Basically, what it is like the core charge distribution there. You can take an average of those 2, and that will give you charge descriptors. If you sum all of them up, it leads to 1,557 descriptors for one material. And we believe that this is a unique representation of the whole compound based on chemistry, charge, and structure. So this is already available in the US NIST/Gov/Jarvis, our GitHub page. And there's another MapMiner package which they have also implemented. I think it will be soon available in the DScribe. I was talking to someone here. They might have this available there too. So we tried this descriptor for around 30,000 materials in this paper. And it consists of not just binary, but other multi-component system as well as multi-atomic system. So as I said, there are 30,000 materials in the data set, right? So you can imagine if we have 30,000 materials and their corresponding 1,557 descriptors, what we are dealing with is 30,000 by 1,557 matrix as input. It's a huge dimension to visualize. So what we do, we use something called T-distributed stochastic neighbor embedding method to nonlinear map this 1,557 by 30,000 into 2 dimensions. And we color code this based on the cubic system. So the reason we are doing this to know whether our data is clustered on a particular system or not. If it's a cluster, then what your interpolation is going to be terrible. You want your interpolation to be well spread. So this is a way to visualizing that our descriptor can capture most of the crystal system there as well. And not just the total descriptor, but also the angle distribution part there only also. And in terms of the data, so I always recommend to first visualize your data. Do a simple histogram plot. Because we know that machine learning is generally good for interpolation, but really terrible for extrapolation. So if you know the range of your data, it really gives you confidence level there too. And these are the 3 for solids. These are the basic models. These are generally termed like formation energy, bandgap, bulk, and shear modulus. What we have added here is some other cool properties too. So like for example, we converge the K point and cutoff for each material using DFT. So we can machine learn them too. We have using constant relaxation time approach and semi-classical Boltzmann transport equation. We have the thermoelectric power factor, Seebeck coefficient, and ZT factor. We learned them too. As I said, we have spectroscopy limited maximum efficiency for solar cell efficiency. We learned them. We have the refractory index. We have 2D exfoliation energies. We have surface energies from elemental crystals. We have a symmetric till grain boundary energy, and as I said, topological spillage for topological materials. I'm going to show how do we learn that too. So first, the classification curve. So the classification basically gives you an interval whether instead of 0 to 1. For example, you want to know whether my material is magnetic or not, whether it's metallic or not, whether it's solar cell efficient or not, whether it's thermoelectric or not. So for that kind of purposes, classification is a good tool as a machine learning method. So here, what I'm showing you is that true positive versus a false positive rate is a way of finding the accuracy of your classification model. So if it's completely 1, the area under curve is a perfect model. If it's 0.5, it's a random guessing. So you can see that our CFIT descriptors really perform well for magnetic system as well as metallic system with 0.96 and 0.95. And not just that, we said for solar cell efficiency, so 0.90 there. And here for N-type power factor, N-type ZT, and N-type Seebeck coefficient, we get around 0.9 accuracy too. So here we're saying that if you give a material, it will quickly tell you whether the material is having high power factor or not, high Seebeck coefficient or not, or high solar cell efficiency or not. In terms of regression, we trained several models. So one of the way to visualize your regression model is first using learning curve. If you want to if you add more data, whether your model is learning more information or not, whether the accuracy, the error of the model is going down or not. If it's not going down, it's not machine learning model straight. If it's going down, then it's learning there. There are chances of learning more. In addition, we do is something called like performance on 10% health set. So it should be a 45-degree line or close to 45-degree line. And we do it multiple times in terms of K-fold validation. So the reason I'm showing this so that people who are actually like beginner in this field must, at least they should do this kind of check before reporting their machine learning model report. So one of the good things of using gradient boosting decision trees, for example, is what we get is feature importance. So for each 1,557 descriptors, we get this, feature importance for all of them. And in generally, they show that using histogram plot, but here I just lump them using their classes. For example, the chemistry, the radial distribution part, the angular distribution part. So what we find very interestingly is chemistry is the most important features for identifying the formation energy, for example. But second comes RDF, radial distribution, angle distribution, and the last was the charge distribution. Similarly, we did something called the feature elimination plot. where we sequentially add more structural descriptor, and we find that the model actually improves its performance. These are some of the models, and we did not just fit 3D, but also 2D exfoliation energy and other properties as well. And we tried, for example, the off-BAT refractive index, TB, MBJ, band gap, and refractive index, and the formation energy, of course. So here's an example of screening semiconducting 2D material using machine learning. So since we had the band gap model, as well as we had the exfoliation energy model, we combined them to find out of, for example, 5,000 material, how many of them are 2D and semiconducting. So using this machine learning step, we can quickly screen around 58 such materials out of 5,000, which will have semiconducting and 2D high exfoliable materials. And we actually validated as using density functional theory, at least for 3 compounds, such as copper, indide, indium, and indium sulfide as 2D semiconducting materials. We applied to the molecules also. So one of the good things about CFIT descriptors, it can be applied for other systems as well. So we applied on 134,000 molecules, and here I'm showing the plots for only the 10% health set, and we find that around 0.97 R square or about chemical accuracy performance. We tried for surface energies for different elements, and up to 0 to 3 Miller indices, and here we found that around 0.13 joule per meter square mean absolute error for surface energy for elemental crystals. We tried for gain boundaries. This is using the classical force field part in addition to the DFT part. So we use symmetric tilt grain boundaries for FCC, BCC, and diamond structure, and we found around R square 0.98. We went much ahead, and we tried for proteins. So we take 10,000 proteins, 630,000 A-flow materials, 360,000 OQMD materials, 111,000 crystallographic open database, 80,000 materials from materials project, 30,000 from JARVIS, and you can imagine as a 1 million rows and 1,557 columns. This is your input matrix. So we converted this huge dimension into 2 dimensions again in t-SNE. So here we are saying that even in that huge space, our descriptor can be identifying certain classes of materials. But should we claim a victory here that our descriptor can do well? No, I was not happy with it. If you are a data scientist, you might be very happy, oh, my R square is good, my MA is good, my RMSE is good. But as a material science, there is some part of you which doesn't accept it there, right? So for that, what I did is I linked the genetic algorithm with machine learning. So in my PhD, I used to develop classical force field, and anytime we develop classical force field, we link with genetic algorithm to map the energy landscape. So if we map an energy landscape, if there's an unreasonable material in our convex cell, then it's not a good potential. So why not try for machine learning? Generally use DFT, MD, why not machine learning? And the idea of genetic algorithm is that you have parent structure and you mate them, combine them, and calculate energies. And if the energy, the lowest energy is basically the materials which survive there. So we calculate energy using machine learning, which is very, very rapid and fast compared to other conventional methods. So here I'm showing you, so basically this model of genetic algorithm plus formation energy can work for any 82 or 83 elements of the periodic table or any crystal structures. But we tried only for example, MOS system, molybdenum system. So what we did, we took all the MO and S and all the MOS parent structure and let it mate with each other. Like you can cut it, some part of it and patch, and then you keep involving for around 5,000 generations of materials. So if you do that, and so this is the convex hull of machine learning, and this is a convex hull of density functional theory. What we find very surprisingly and very interestingly is that the MOS2H structure, which is supposed to be in reality the most stable phase of MOS2, was actually stable in machine learning model too. So again, in conventional like DFT or classical potential, there is a governing Hamiltonian there, which helps you like constrain the space of the materials. But here in data-driven approach, there was no such constraint, but still it was able to find MOS2 on the convex hull, which is very promising to me. And our colleagues at several universities are trying to design different high entropy alloys using this kind of method. So what they want to do is like they let it mate all the different elements for like high entropy alloys, and whatever the lowest energy structure, they calculate the DFT data for those only. So these are demo, for example. If you put your material in terms of postcard format, It predicts you, for example, band gap, the cutoff needed, the k-points needed, the refractive indices, and other properties there. And it's fun. I mean, I'm having a lot of fun working on this kind of project. So in summary, I would like to say at least take two things from this lecture: the unified C-feed descriptors and the Jarvis database and tools. No matter what area of research you are working on, I believe that this will be useful to you. And we have already in 2-3 years, we have around 40,000 user views. So we count all the user view there. And I'm very excited about something called Jarvis Voice, where you can talk to database and it will tell you the properties and predict properties using just voice recognition. It is coming soon, maybe next month. I'm writing a paper on it right now. And there's a phase-filled finite element and Jarvis experimental database also coming there. We are organizing something called Artificial Intelligence for Material Science workshop on August 1st and 2nd. And if you are interested, it's free registration. I invite you to come there. These are homepage, jarvis.nist.gov, or you can we are a Google generation, so we can just Jarvis NIST and we'll show you our website. And most of my slides are available on this slideshare.net. And especially, I would like to invite the young generation of the crowd to basically use these kind of tools and help us improve the tools. And having something like open access data and tools is definitely a good way to start using that direction. With that, I'd like to thank you for your attention, and I'll be happy to answer any questions.
Nice talk. Directly.
Quick comment. So as part of Airflow, we've done a lot of machine learning as well. And one of the reasons why we don't use structural descriptors, because you have to know DFT optimized structure to get your structure-based descriptors. So now, if you do have DFT optimized structures, I mean you already run quantum mechanics, and then you don't need prediction of your DFT energy anyway. So when you have a new material, you will not have DFT structure. So how you solve this paradox?
Yeah, here the genetic algorithm will be helpful. So basically, suppose you want to design a nickel aluminum system, or nickel aluminum cobalt. Take 5 components: nickel, aluminum, chromium, iron, whatever 5 elements. You want to find a golden additive manufacturing alloy there. What you would do is you let them combine using genetic algorithm and machine learning model and find your convex hull. And on the low energy state, it will predict the structure also. So there you will do only DFT calculation on low lying structures. And based on that, that will give you what is your favorite alloys in that composition. So this is a kind of inverse problem you're asking, right? So if you
no. In the prediction models, not in this, right? When you predict band gap, right?
Yeah. So suppose so I think if I understand correctly, you're saying that.
So your feature encode structure exactly DFT structure, right?
Yes.
But if somebody comes to you, I don't know, uranium oxide, which you never knew the DFT structure before. So somebody can draw you a plausible structure, but you will never know exact DFT structure.
Yes, it's very difficult to know. It's a hard problem. But what I'm suggesting here is like you can take uranium and oxygen structure, right, which is available, and you can let it combine with like using genetic algorithm and see in the convex hull where the structure lies for U or 2, and you can actually validate using density functional theory whether that's so. And then you can do experiment like XRD or stuff like that, TEM, to actually see the structure experimentally. That would be one route, I believe.
We can talk.
So there's one more question. Yeah. Be prepared to catch the mic.
Thanks. So the ROC curves are used to find the best threshold decision for your classifier. So why do you have ROC curve? Why do you need ROC curve? You have a classifier, but what is the parameter that you're trying to optimize to have the best sensitivity and specificity for your classifier?
So so if I understand your question correctly, you're asking why do we need ROC curve?
Yeah. So if you're plotting ROC curves in order to find what is the best threshold decision to have the best sensitivity and specificity of your test. So what is this decision threshold?
So what we notice is the area under curve, right? You're familiar with this topic, right? Area under curve?
Yeah, I know very well what.
Yeah. So
I don't understand why you are plotting rock curve.
So the reason we are predicting is, suppose this is the performance on that. Suppose you have new crystal structure, and you just want to know whether it's metallic or not. Then if your rock curves gives very high area under curve, then it can quickly predict the band gap. Whether not predict the band gap, it will tell you whether it's metallic or not. It will quickly predict and classify material based on if you have good rock curve area under curve. If it's like around 0.5, there's no point using that classification model. So if you go to for example, if you go to the JARVIS-ML site, if you put a structure, it will tell you whether material is solar cell efficient or not, just using the classification rock curve analysis.
Okay. And do you have balanced data? I mean, you are trying to, the first one, for instance, you are trying to predict whether it's magnetic or not.
Yeah.
But in your input data, did you have a lot of magnetic, as much as magnetic materials than as not magnetic material?
Yeah, yeah. We have around 50-50 kind of thing.
Okay, great. Thanks.
So I think if there's no more urgent question, then we move on. So let's thank Kamal again.